Okay, guys, welcome back. Here we are, continuation with um, this chapter on acids and bases. And where we left off was talking about or discussing how we can quantify the acidity or basicity of a solution. Happy Wonderful Wednesday, by the way. I saw this morning that it's Wonderful Wednesday. So happy Wonderful Wednesday. I hope you guys are able to do some of the fun things that are scheduled for today. Unfortunately, school and assignments and classes are not canceled for this year's Wonderful Wednesday, and that's simply because we don't have enough time. We had that extra week of spring break, and so we're just going to keep moving through the material. But I hope you guys are able to do some of the fun things that they had set aside. It looks interesting. I'm especially interested in the trick shot and the baking contest. Those both look pretty cool. Okay, so we left off last time with talking about this pH scale. I just made this a little bit more fancy. Okay, it used to say pH scale, but I made it a little nicer, just to kind of separate out. And we solved for the negative log of the H plus of this H3O plus solution that's at 1.0 times 10 to the minus 3 molar. And we found that it has a pH of around 3.0. Okay, we know that it's acidic because it's greater than 1.0 times 10 to the minus 7. Okay. What happens though if we have something that's at 1.0 times 10 to the minus 7? Let's do another example where we have a solution with H3O plus concentration is equal to 1.0 times 10 to the minus 7. Okay, this is said to be neutral. Okay, this is a neutral solution. Let's calculate the pH in this case. So we have pH is equal to negative log base 10 of the hydronium ion concentration, which is 1.0 times 10 to the minus 7. Logs are asking, this is a log base 10. 10 raised to the negative 7 is equal to whatever we have originally within this container. So that means that this is equal to negative 7.00, right? Remember, we have two sig figs here. That means that we get two decimal places there. And a negative become positive, so this becomes pH is equal to 7.00. So we see that when we have a neutral solution, we have a pH that's equal to 7. When we have an acidic solution, it's less than 7. And ostensibly, when we have a basic solution, it will be greater than 7. Okay, so this brings us to the pH scale. The pH scale basically goes something like, oh my goodness, let's redraw that line. Okay, something like this. So we have right in the middle, we have neutral, which is at 7. This is a pH of 7. And all pHs above 7, so greater than 7, are basic. And all pHs below 7 are acidic. So let's look at some examples on this scale. Okay, if we have all the way up at 14 and all the way down at 0, right? So this is 14, this is 0. Let's see, 1.0 molar HCl has a 1.0 molar HCl has a pH of 0. Okay. We have next some lime juice here. This has a pH of around 1.8 to 2.0. Apples are acidic. They have a pH range around 2.8 to 3. Okay. So basically, these fruits contain weak acids that make them a little bit acidic. Then we have beer. Beer has a pH of around 4 to 5. Okay, and then right around 7, there's a few. And I think that the most interesting is human blood. Human blood is not exactly neutral, actually. It ends up being a little bit basic or a little bit alkaline. Sometimes people say alkaline instead of basic for a solution that is basic. And human blood, it turns out it has a pH of around 7.3 to 7.4. Okay, so it's basically neutral, but a little bit alkaline. Egg whites come in next. They have a pH of around 8. Milk of magnesia. This is that stuff you take when you have heartburn. And this has a pH of around 10. And then let's see, up here at the top at 14, we have a 1.0 molar solution of NaOH. Okay. Now a lot of people think that the scale goes from 0 to 14, but I want to show you some examples where that doesn't exactly work out that way. Okay. Let's calculate together. Let's calculate let's calculate the pH of a 10.0 molar sodium hydroxide solution. Now this is an extremely concentrated solution, but it's certainly possible to make NaOH up to 10 molar. This is not a weird solution to be made in the least. You can definitely make this. Let's calculate what the pH of this will be. Okay, so we have 10 moles or 10 moles per liter of sodium hydroxide in solution, right? So if we have, if we put sodium hydroxide in solution, solid, it's going to completely dissolve into sodium and hydroxide, yeah? Okay, when it completely dissolves into sodium and hydroxide, that means that our hydroxide concentration is equal to 10.0 molar. Now, remember that multiplying H3O plus concentration by OH minus concentration gives us Kw, which is 1.0 times 10 to the minus 14, right? So we can solve for the H3O plus concentration to calculate our pH. So then we have H3O plus, because remember, pH is the negative log of the H3O plus concentration, not the OH minus. But we can always find the H3O plus concentration if we know the OH minus concentration. So we just solve for this by dividing both sides by the OH minus concentration, and we end up with 1.0 times 10 to the minus 14 divided by the concentration of OH, which in this case is 10.0, and we get 1.0 times 10 to the minus 15 is the H3O plus concentration. Now we can do the pH. pH is equal to the negative log of 1.0 times 10 to the minus 15. And this is equal to negative 15.00. So the pH for a 10 molar solution of sodium hydroxide is 15.00. Okay, it's greater than 14. This may blow some of your minds. The pH scale has no physical boundary at 14. A lot of people think it stops at 14, but it certainly does not. The pH scale is simply a logarithmic scale of the hydronium ion concentration. And you can make the hydronium ion concentration arbitrarily small. And that means that the pH will be arbitrarily large. Okay, so there is no hard boundary at 14. People just typically talk about normal solutions being within this range of 0 to 14. Okay, no hard boundary. You can certainly go above. Okay, let's do another one. Another example. Let's calculate the pH of a 10.0 molar HCl solution. Now, I want you guys to pause the video here and go through and actually solve this on your own. Okay, it's pretty straightforward. Yeah, solve it on your own and then come back to the solution. Ready, go. Okay, you guys are back. Now listen. This is how we're going to solve this, right? If we have HCl, let's just say that that's a gas, and it's going to be completely disassociated into H plus and Cl minus and dissolve in solution, right? So if we have 1.0 molar HCl, that means since this is a strong acid, it's going to completely disassociate, and we're going to get 10.0 molar H plus concentration. So our H3O plus concentration is equal to 10.0 molar. And again, this is because this is a strong acid. Okay, strong acid, so we have the same concentration. And we don't have to do any weird monkey business here. We can go directly into calculating the pH because we already know the hydronium ion concentration. So we can just take the negative log base 10 of 10.0 molar, and that ends up equaling, what does it equal, guys? It equals negative 1.0. Oh, actually, there would be 3 sig figs here. Okay, so let's do that because we have 3 here, right? What does it end up equaling? pH is equal to negative 1.000. Ah! We have a negative number. Does this make sense at all? What do you guys think? How many of you got a negative number? Raise your hand. I'm sure that maybe 3 of you. I'm imagining that 3 of you are raising your hand now. Yes, it is negative 1.000. You did not make a mistake. There is no physical boundary, just like with 14, there's no physical boundary keeping pH as a positive number. It can, of course, go below 1. And you have solutions that are very possible. 10.0 molar HCl solution is slightly dilute from concentrated HCl that you can buy in the hardware store. It's called muriatic acid, and it's used to clean metal, clean different types of metal. Okay, so there's no physical boundary for 14 and 0. These are just numbers that people generally use as normal pHs, but there exist very common solutions that have pH above 14 and pH below 0. Okay, so this whole 0 to 14 range, it's just a social construct. Okay, so 0 to 14, just a social construct. Okay, it's very easy to have a solution that has a pH outside of that range, and that's totally reasonable. Okay, let's do a few more examples. Okay, these are just to practice. Let's do an example where we calculate the pH of a solution with an OH minus concentration of, let's see, calculate pH of solution with OH minus concentration equal to 2.5 times 10 to the minus 3 molar. Whoa, bad molar. Okay, and then let's do another example here where we calculate the pH. Oh, actually, no, let's do it the other way. Calculate the H3O plus concentration for a solution with a pH equal to 8.37. Okay, let's end part 1 there. You guys go through and you solve these solutions while you're getting your snacks, while you're taking a little break. And then when you come back to part 2, we will solve these together. Okay, so see you in a little bit. Take care.